Let's look at two special cases of rectilinear motion. First is uniform rectilinear motion. Now that term is a specialized term, uniform rectilinear motion. If we say that, what it means is this, is that the velocity is constant. So we could write it this way. dx dt, remember that velocity, and that's going to be a constant value. Now, if that's constant, that implies something else. What does that imply? It implies that the acceleration, which is dv dt, what's the time derivative of a constant? The acceleration is going to be 0. And because of that, we could write the equations of motion with this special equation as this. X as a function of time is just going to equal some initial x naught, we'll call it, plus the velocity times time. Now, and in this case, the velocity is a constant, so that's just some number. So given the time, we can easily write down the position. Now the second special case, remember, so we've got the first special case, that term means something special, uniform rectilinear motion. The second term also means something special, uniformly accelerated motion. Now, uniformly accelerated motion means this. It means that the acceleration, which is dv dt, or the second derivative of the position, is going to be a constant. And so, just like above, we can write this with a special equation where we know that the velocity is going to be equal to some initial velocity v naught plus the acceleration, which is just a constant, times the time. And then we can write the position this way. X is going to equal the initial position, x naught, plus v naught times the time plus a half times the acceleration times the time squared. So the point of this is that there are special cases of rectilinear motion, and if you hear this phrase, uniform rectilinear motion, it means that the velocity is constant and these equations apply. If you hear this term, uniformly accelerated motion, that means the acceleration is constant and these equations apply. So these are two special cases of rectilinear motion.